Welcome to Lecture 32. This is our second to last lecture on time-dependent problems. We're going to be covering two different topics in this lecture. The first one is called Fermi's Golden Rule, and this is the way that you calculate the rate for a transition from a bound state to the continuum. And the second is called the sudden approximation. This is what you do if you assume that the change in the Hamiltonian occurs instantaneously fast. All right, so let's get started. When we first discussed time-dependent perturbation theory, we found that the probability for a transition from state M to state N in the first Born approximation was given by this simple integral formula. So the probability from M to N as a function of t is 1 over h bar squared, the absolute value magnitude squared of the integral from t0 to t dt1 e to the I omega nm t1 minus t0, the matrix element vnm of t1 whole modulus squared. Now I want to remind you omega nm was the difference in energies between the states n and m for the unperturbed Hamiltonian divided by h bar, and vnm is the matrix element of the time-dependent perturbation with respect to the unperturbed eigenfunctions labeled by n and m. Now, if we look at a situation where the Hamiltonian v is independent of time, then all the time dependence in that integral is in the exponential, and I can immediately do the integral. We're also going to set t0 equal to 0 for convenience, and we did this also in an earlier lecture, and the result that you get is it becomes 4 sine squared omega nm t over 2 divided by h bar squared omega nm squared multiplied by the matrix element vnm modulus squared. And this was the result that we got for a discrete spectrum. We'd be looking here at transitions between two different discrete eigenstates n and m. The whole idea of Fermi's golden rule is that we're going to generalize this from a discrete spectrum to a continuous spectrum. So what we're going to think of initially is let's just replace this omega nm, which was a discrete energy difference between the two states, by a free variable omega. If I'm in the continuum, the states have any possible energy in the continuum, and I would then express this difference in terms of some continuous parameter omega. And so let's just plot that function replacing omega nm by omega. So f of omega is 4 sine squared omega t divided by 2 divided by h bar squared omega squared, and the plot is given for you on the right. You can see it's strongly peaked around omega equals 0, because near omega equals 0 you can calculate the sine omega t divided by omega will go like t over 2. If I square that, I'll get t squared over 4. That cancels the 4 and it becomes t squared over h bar squared. And so the peak is going to be t squared over h bar squared. And then it's always positive because it's the square of a function, and it's going to have some oscillations because we know the sign goes to 0, so it's going to look kind of like this plot is showing you. Now, if I take the limit t goes to infinity, you see that central peak at omega equals 0 is going to grow to infinity. So that suggests that this f of omega is going to behave like a delta function, and our guess is that it's going to behave like c times t times a delta function. Now, if I look at the integral of d omega over all omega, that's a function that I can exactly integrate, and you find it's equal to 2 pi t over h bar squared, and that tells you that the constant c is 2 pi over h bar squared. So what we have learned, if we take the limit t goes to infinity of this transition from state m to n as a function of time, it'll go like a matrix element squared divided by h bar squared times 2 pi t times a delta function of en of 0 minus em of 0 over h bar. And I can remove the h bar in the denominator of that delta function to rewrite it as 2 pi over h bar t delta of en of 0 minus em of 0 multiplied by vnm squared. That's just using the identity that the delta function of c times t is equal to 1 over c, the delta function of t. All right, so we have worked out a formula here, and you can see that the probability is increasing linearly in time. Let me show that to you again. you can see it's got a t in front of it. So the probability is increasing linearly in time. And what we do is we actually look at the rate at which the probability increases. And that's given by the time derivative of this transition as a function of time. And that's just equal to 2 pi over h bar delta En of 0 minus Em of 0 times this matrix element Vnm squared. That rate is a constant. And so what this tells you is when I'm having transitions via time-dependent perturbation theory in the long time limit, the transitions are governed by a constant rate. Now in the continuum, all energy levels are allowed, so we can drop the subscript 0. We can let n be replaced by f, which stands for final state, m by I, which stands for the initial state, and we get that the rate p dot, the transition from the initial state to the final state as a function of time, is 2 pi over h bar delta of ef minus ei multiplied by the modulus squared of vfi. This formula is a very famous formula, and it's called Fermi's golden rule. It turns out that, as with many things, this was actually first derived by Dirac, and we really should be calling it Dirac's golden rule. Apparently it's called Fermi's golden rule because Fermi really popularized the result. I'm guessing Dirac didn't think it was such an important result, but Fermi did, and so it now goes by the name Fermi's golden rule. Now, as we were talking about before, when we do time-dependent perturbation theory, we do have to worry about the fact that if I'm doing transitions from a state, eventually at some point there's nothing left for me to have transitions from. That's called the depletion problem. And sometimes, in order to solve that depletion problem, in a completely ad hoc way, we add an extra factor of p on the right-hand side of that rate equation. So we would then get p dot, the transition from the initial to final state as a function of t, is 2 pi over h bar delta ef minus ei vfi modulus squared times p of t. Now that, as a differential equation, we know the solution of that if the matrix element is independent of t, which is what we assumed. That's just an exponential function that solves that differential equation, and in that case the probability will always be bounded. So let's try and go through an example of how this might work. We're going to consider something, it's a bit of a contrived example, but it's something that illustrates these principles, and it also is kind of an interesting physical problem, so we're going to focus on that. We're going to consider a helium-like atom, so the nucleus has 2 protons in it, and it's going to have, instead of 2 electrons orbiting it, it's going to have a muon and an electron orbiting it. We're going to use capital letters to describe the muon variables, lowercase letters to describe the electron variables. And so the Hamiltonian will be h hat is little p squared over 2m minus ze squared over r. Z is going to equal 2 in this case, plus big P squared over 2m minus ze squared over big R, plus e squared over the difference in the two r's. That's the difference in the two vector r's. That's the Coulomb repulsion between the electron and the muon. Now the one thing that we have to recognize is that the mass of the muon is more than 200 times larger than the mass of the electron, and that tells us that the Bohr radius for the muon is 200 times smaller than the Bohr radius for the electron, and so the muon is going to orbit much more closely to the nucleus. So really what we should think of is a muon orbiting a helium nucleus, and then the electron is going to act essentially as if the nuclear charge is approximately equal to 1 for the electron. Now this is not an exact approach, but it's a pretty clear picture of what is going on. We essentially can assume that the R, the big R that goes in that Coulomb repulsion term, e squared over little r minus big R, we can just replace the big R by 0, and then that will be one term that cancels one of the minus ze squared over r terms that would correspond to the attraction with the nucleus. And so let's illustrate how that works. We rewrite the Hamiltonian as an h0 plus a v, where the h0 does exactly that. We have a little p squared over 2m minus little e squared over r plus big P squared over 2m minus 2e squared over r plus e squared over big R minus e squared over little r, and we call that v, and v is very small. That's a perturbation. The unperturbed wave functions of this are an electron in a hydrogen field and a muon in a helium field, and we can easily calculate what the energies are going to be and what the wave functions are. we have a separation into a product of two different wave functions for the muon and the electron. So there's one term that will be in a helium field, that's for the muon, and one that's in a hydrogen field, that's for the electron. The energy will be the standard formula that we found for hydrogen, which we can write as minus m over e to the fourth divided by 2 h bar squared n squared, that's for the electron, and then minus 2 big M e to the fourth over h bar squared n prime squared, that is for the helium. The 2 is in the numerator because we had a z squared divided by 2, and z is equal to 2, so z squared divided by 2 is equal to 2. Now the ground state corresponds to both of those integers equal to 1. We're going to put both states in the ground state, and we can calculate that ground state energy. It's minus e to the fourth over 2h bar squared little m plus 4 big M. If we look at an excited state where we move the muon into its 2s state, or 2p state, then we have n equals 1, n prime equals 2, and that has an energy minus e to the fourth over 2h bar squared little m plus big M. If we look at the energy difference between those, that is equal to 3 big M e to the fourth over 2h bar squared. So suppose the system starts in an excited state and it's going to drop to the ground state. If the electron absorbs this energy, so this is something that we could have happen. The electron is in the ground state initially. The muon is in its first excited state. The muon goes to the ground state, and that energy can either be emitted in a photon, and that photon would then take all the energy away, or the electron could absorb that energy. Instead, that would be called a non-radiative transition. But if the electron absorbs that energy, its total energy is much, much larger than 0. So the electron would go into an unbound state, and it would be ejected from this system. And that is a transition that's a very important transition in many different solid state and atomic situations. It's called an Auger transition. Because the phase space for these transitions can be higher than the phase space for a photon being ejected, these can often be the prevalent transitions that occur for different experimental situations. So let's suppose at time t equals 0, we're in the state n prime equals 2, n equals 1. That means the muon is in the n prime equals 2 shell, and the electron is in the ground state. What is the rate for the electron to be rejected at large time? Well, to get the rate, we just use the Fermi golden rule, 2 pi over h bar VFI squared delta EF minus EI. Our initial energy is the energy minus e to the fourth over 2h bar squared little m plus big N. The final energy is minus e to the fourth over 2h bar squared 4m plus h bar squared k squared over 2m. Since we assume the electron is so high energy, it's essentially a free particle and it doesn't feel the pull of the nucleus at all. And so we can write our initial state as a U2LML of R, and our electron state is in the 1s state, so it's U100 of R. The final state is U100 of big R, and then e to the ik dot r because the electron has been put into a plane wave state. We're going to sum over all of the final momentum to get the total rate, so we're not going to worry about exactly what k state it went into. Of course, energy conservation is going to primarily put the electrons into states that all have about the same energy. The sum over k, as we know, will go to 1 over 2 pi cubed to integral d cubed of k. And so we can rewrite the rate as the integral d cubed k over 2 pi cubed. We put now in the Fermi's golden rule, 2 pi over h bar, the modulus squared of the matrix element, a delta function of EF minus EI. Now d cubed k, we can write that as k squared dk d omega. We can write that as k dk squared over 2 d omega. And we can just recognize epsilon k is equal to h bar squared k squared over 2m. So we can rewrite that as 2m epsilon k over h bar squared square root m over h bar squared d epsilon k d big omega. Omega is the solid angle. We recognize that epsilon k is really the final energy, so we write d epsilon k is equal to d epsilon f. The delta function is going to be something that can then be integrated. We can do the integral over energy. leaving behind the integral over solid angle. So let's write down what that integral is. It's integral d epsilon f over 2 pi cubed, d big omega, 2m epsilon k over h bar squared, m over h bar squared, 2 pi over h bar, v fi of k quantity squared, delta ef minus ei. We simply set ef, which is equal to epsilon k, equal to e initial. So we get integral d omega over 2 pi cubed, 2m e to the fourth over 2h bar squared, 3 big M minus little m over h bar squared to the 1/2 power, m over h bar squared, 2 pi over h bar, multiplied by this matrix element squared, which is a function of k. We can pull out all of our factors. We get 1 over 2 pi squared, h bar to the 5th, e squared m, square root of m, quantity 3 big M minus little m, integral d big omega v fi of k, modulus squared. So we need to figure out what that matrix element is. The matrix element squared is equal to an integral over the muon coordinates of u2l ml of r, u1 0 0 of r, big R. That's looking at the initial and final states of the muon. And then integral d cubed e to the minus I k dot r u1 0 0 of r. That's looking at the initial and final states of the electron. And then it's multiplied by the v, which is e squared over big R minus e squared over little r. And that's a term that's going to be non-zero only if ml is equal to 0. Okay, so to complete the problem, one would have to actually work out what that integral is. We're not going to go through those details here. All right, let's now move on to the sudden approximation. This is now a completely new topic. We suppose that the system is given in a time-independent potential for t less than 0, and then we say at t equals 0, the potential suddenly changes to a new potential, and it remains in that new potential for all t bigger than 0. And the question we want to ask is what happens to the states of the quantum system? Now in practice, no potential changes instantly, but these changes can be very fast. Take, for example, something like a radioactive decay. We can think of something like the beta decay of tritium. So tritium is an isotope of hydrogen that has 1 proton and 2 neutrons in the nucleus. And what happens is the neutron emits an electron and a neutrino and converts from a neutron into a proton. And so we have a conversion from a hydrogen nucleus into a helium nucleus. And that decay can be very, very rapid. And so using this sudden approximation is a good approximation for these kinds of transitions that can be very rapid. So what is it we're going to do? We're going to first find the eigenfunctions of the Hamiltonian for early times before the system changes. We'll call those eigenfunctions psi I. And we're going to find the eigenfunctions of the Hamiltonian h bar, which corresponds to the times bigger than 0. We'll call those eigenfunctions psi f. And the probability to find the system in one of the f states, if it started in an I state, is simply the overlap squared of that matrix element. So the probability to go from the initial state to the final state is just the modulus squared of the overlap of the final state with the initial state. And it's that simple. That's all it is to the sudden approximation. Essentially what we're saying is we started out in some state, our initial state, and we now need to decompose that initial state into the eigenfunctions of the final state. And the modulus squared of that overlap tells us how much of the initial state is represented in the final state eigenfunctions. And this is just a very simple way of thinking about and understanding how such a problem works. So for this one, we're going to work on an example. This is a rather contrived example, but it's one that you'll find in many different textbooks. We start with a particle in a box of length L, and we assume that it starts in the ground state. And then we say at time t equals 0, the box increases in size to 2L suddenly. What is the probability to be in each of the eigenstates of the wider box? Now, since we know both of those systems have a complete set of eigenstates, if I'm in some state inside the bigger box, which is given by that ground state wave function of the smaller box, it must be expressed in terms of a linear combination of all of the eigenfunctions of the bigger box. So this problem has a nice simple resolution. Just work out what it is by carefully looking at the eigenfunctions for both of the particles in a box. So the eigenfunction, the nth eigenstate of a particle in a box is given by square root of 2 over L. The normalization factor does not depend on n, multiplied by sine n pi x over L, where n runs from 1 to 2 all the way out to infinity. That would be for the box that is of length L, and remember that the way that this wave function is written, we're starting at 0 and we're going to L. The wave function is equal to 0 in the range where x is bigger than L out to 2L. Now the final wave functions are given by just taking L goes to 2L. So I get 1 over the square root of L sine n pi x over 2L, where now n runs from 1 to 2 out to infinity. And so now we just have to calculate the overlap of this and square it. So the overlap is given by an integral from 0 to L. I only need to run out to L because the initial wave function is 0 running from L to 2L. So that will not contribute anything to the integral. I have the initial wave function, which is square root 2 over L sine pi x over L. I have the final wave function, which is square root 1 over L sine n pi x over 2L. We now use a angle, sum, and difference formula to replace the product of two sines by the difference of two cosines. So we first pull out a factor of square root of 2 over L, and when we square that, we get 2 over L squared, and then we have left behind this modulus integral dx. The trig relation is going to tell me that that integrand, sine pi x over L times sine n pi x over 2L, becomes 1/2 cosine n plus 2 pi x over 2L minus cosine n minus 2 pi x over 2L. We can factor the 1/2 out. That gives a 1/4 when it's squared. I get a 1 over 2L squared. We can do each of those integrals. The first one is 2L over n plus 2 pi sine n plus 2 pi x over 2L minus 2L over n minus 2 pi sine n minus 2 pi x over 2L. And we have to evaluate that between 0 and L. At 0, the signs are all equal to 0, so we only really have to evaluate it at L. And what we find, it's equal to sine n plus 2 pi over 2 multiplied by 1 over n plus 2 minus sine n minus 2 pi over 2 multiplied by 1 over n minus 2. And then we have a factor of 2 over pi that we pulled out. That becomes 4 over pi squared. And we also pulled out a factor of L, which became L squared. So the prefactor now becomes 2 over pi squared. And we have this modulus of sine of n plus 2 pi over 2, 1 over n plus 2 minus sine n minus 2 pi over 2, 1 over n minus 2. And one case we have to be very careful of is the case n equals 2. So let's look carefully at the integrand when n equals 2. When n equals 2, that cosine of n minus 2 pi x over 2L, that just becomes 1. And the integral of 1 is just going to become L. And so we have to carefully work out that relation in the case when n is equal to 2. All of the other cases we can work out, we can use the formula. So when n is even and n is not equal to 2, that integral is equal to 0. When n is equal to 2, you can work out that the integral is equal to 1/2. You can see that in that case, it's just an integral of sine squared pi x over L from 0 to L. And when n is odd, we find it's equal to 32 over pi squared n plus 2 squared n minus 2 squared. Okay, so we've gotten the exact answers for these probabilities. Let's verify that this actually works. One check that we can do is if I sum this overlap over all n, the modulus squared, that has to equal 1. That has to equal 1 because I'm essentially summing the coefficients of the wave function of that initial wave function now represented in the final eigenstate basis. And the first term that we're going to get from that is a 1/2 from n equals 2, and then we have a sum over all of the odd terms. That's going to be plus 32 over pi squared, the sum n equals 0 to infinity, 1 over 2n plus 3 squared multiplied by 2n minus 1 squared. Now it turns out you can exactly do this sum, and it just takes a couple of different steps in order to get there. So the first thing we have to do is use partial fractions to separate out the two different factors. And you can immediately see you can rewrite 1 over 2n plus 3 squared times 1 over 2n minus 1 squared as 1 over 2n plus 3 squared minus 1 over 2n minus 1 squared divided by a correction factor, which is the numerator that I get when I evaluate that sum or that difference and put both of the terms in terms of a numerator and a denominator. And it turns out that that correction factor is minus 8 times 2n plus 1. So we can pull that factor out. I'm going to leave the minus sign inside the summation. I'm going to pull the 8 out. I have to leave the 2n plus 1 there as well. So I get 1/2 plus 4 over pi squared sum n equals 0 to infinity, 1 over 2n minus 1 squared multiplied by 2n plus 1 minus 1 over 2n plus 3 squared multiplied by 2n plus 1. Again, we're going to use partial fractions, and we're going to re-express this as 1 over 2n minus 1 times 1 over 2n minus 1 minus 1 over 2n plus 1 times 1/2 minus 1 over 2n plus 3 multiplied by 1 over 2n plus 1 minus 1 over 2n plus 3, again multiplied by 1/2. And we now collect up all of our terms. We have a set of terms that are perfect squares, 1 over 2n minus 1 squared plus 1 over 2n plus 3 squared. And then we have terms that still involve products, 1 over 2n minus 1 times 1 over 2n plus 1, and 1 over 2n plus 3 multiplied by 1 over 2n plus. We use partial fractions again on those two terms. We'll get a 1 over 2n minus 1 minus a 1 over 2n plus 1 multiplied by minus 1/2, and a 1 over 2n plus 1 minus a 1 over 2n plus 3 multiplied by minus 1/2. You see that these common factors of 1 over 2n plus 1, those cancel. We also have then these factors that go like 1 over 2n minus 1 and 1 over 2n plus 3. Let's focus in on those. What we need to do is we need to do some shifting of the indices. So if I look at the terms 1 over 2n plus 3, when it's 0, that term starts at 3. And then the next term is going to be 7, and so forth. When I look at 1 over 2n minus 1, that term starts off at 1, and then that term has another term. When n is equal to 1, it's equal to 1 again. And then after that, from terms 2 and above, it is equal to then 3, and then 7, and so forth. So it has two terms that are different, and the rest are the same. So I can combine both of those as 2 over 2n plus 1 quantity squared. And think carefully about, that's the combination of those two terms. Think carefully about how I did that. And then we can look at these other two terms, which is minus 1 over 2 times 2n minus 1 plus 1/2, 1 over 2n plus 3. Again, you can see that there's going to be a cancellation of nearly all of those terms. I simply have to worry about the case when n is equal to 0 and n is equal to 1, but you see in those cases one of those terms will be minus 1, the other one will be plus 1, so those two terms cancel as well, and the net effect is those terms that go like 1 over 2n minus 1 and 1 over 2n plus 3, they both cancel each other out. I'm just left with the sum of the squares, and so I have the sum of the odd squares. The sum of the odd squares, that has a known result. It's equal to pi squared over 8. So when I take the 2 out, that gives me 4 over pi squared. The sum of over those odd integers is pi squared over 8. The net effect is that that whole thing is equal to 1/2. I get 1/2 plus 1/2, and that's equal to 1. And so we've actually shown that the sum of these probabilities is equal to 1, as of course it must be. But it's nice sometimes to be able to check that a complicated formula like this actually turns out to give you 1. Now, if you didn't like going through this in detail, you can take that expression and substitute it into Wolfram alpha, and I believe it will be able to give you that that summation would equal 1 as well. But be careful and make sure that it's properly evaluating everything in the correct way to verify that it does work. I have not tried to do that, but if you're interested in trying to figure out how to do that on your own, I encourage you to give it a try. One doesn't have to necessarily work everything out analytically. We have these nice tools that do allow us to do some of the algebra for us, and it's very beneficial to learn precisely how to use them and use them efficiently and effectively. Okay, that's all that we have for this lecture. We'll see you back with Lecture 33, which is going to be discussing photoproduction of hydrogen. This will be essentially our last time-dependent problem that we're going to be working on in the class. It's going to close out the time-dependent unit. It is going to be looking at a very important problem, which is telling us what are the rates for different excited states in hydrogen to decay. And with that, we'll see you next time.